In 1928, a nearly deaf Russian schoolteacher sat down with a pencil and worked out what it would take to reach another star. His name was Konstantin Tsiolkovsky, and he had already derived the fundamental mathematics of rocket flight before anyone had launched anything, so he was not guessing. The answer his own equations gave him was one he could not soften. The journey would be longer than a human life, so he described the only solution the arithmetic allowed, a vessel where people are born, grow old, and die in transit generation after generation. He called it a Noah's Ark. Nearly a century later, after nuclear pulse propulsion, after fusion drives, after antimatter and laser sails, nobody has improved on his answer. Every serious crude design still needs between 1 and 400 years to cross 4.24 light years, which means the first ship we send to Proxima Centauri will not carry a crew, it will carry a lineage, and by the end of tonight you will know exactly what is waiting for them when it finally stops. Get comfortable. If you would rather know what a journey actually costs than be told the comfortable version, a slow like and subscribe helps this channel reach more curious minds like you. Because by the end of tonight, the most hopeful story we tell about leaving Earth will have quietly become a very different one. Now, let's ease down into this. There is one star that matters more than all the others, and it is not the brightest or the largest or the most beautiful. It is simply the closest. Proxima Centauri sits 4.24 light-years from where you are sitting right now, and that number is the single most important figure in the entire question of whether human beings will ever leave this solar system. Everything else is negotiable. Distance is not. 4.24 light-years. Written out in kilometers, that is roughly 40 trillion. 40,000 billion. If you shrank the sun down to the size of a grain of sand and set it on a table in front of you, Proxima Centauri would be another grain of sand about 40 kilometers away, with nothing whatsoever in between. Not dust worth mentioning, not gas worth mentioning, just the emptiest space that exists anywhere in the universe, stretched across a distance that our instruments can measure precisely and our bodies cannot survive. What makes Proxima strange is that it is both our nearest neighbour and completely invisible to you. You cannot see it. You have never seen it. Step outside on the clearest night of your life, at the darkest site on Earth, with perfect eyes, and Proxima Centauri will not be there. Its apparent magnitude is 11.13, which places it roughly 100 times fainter than the dimmest star the human eye can detect. Our closest stellar neighbour has been sitting there for the entire history of our species, and no human being ever saw it until a telescope was pointed at the right patch of southern sky in 1915. The reason is that Proxima is small. It is a red dwarf, spectral class M 5.5, carrying about 12% of the Sun's mass and roughly 14% of the Sun's radius. If the Sun were a football, Proxima would be about the size of a plum. Its surface sits at around 3040 Kelvin, which is cool as stars go, cool enough that it burns a sullen orange-red rather than white. It fuses hydrogen so slowly and so grudgingly that it will still be shining in 4 trillion years, long after the Sun has died, long after most of the stars you can see tonight have gone dark. It is the most patient object within reach. It does not travel alone. Proxima is gravitationally bound to Alpha Centauri A and B, the bright double star that dominates the southern sky, but bound at a distance so absurd that astronomers argued about it for decades. The separation is roughly 13,000 astronomical units, which is to say 13,000 times the distance from the Earth to the Sun. One orbit takes something on the order of 550,000 years. Proxima is a moon in the loosest possible sense, circling its companions on a timescale longer than the existence of our species. And for most of the 20th century that was the whole story. Proxima Centauri was a small red star that happened to be nearer than the others, and the fact that it was nearer was interesting to precisely nobody outside of astronomy. There was nothing there. It was a destination without a reason. That changed on the 24th of August, 2016. The European Southern Observatory announced the result of a campaign that had been running for months called Pale Red Dot. Using the HARP spectrograph at La Silla in Chile, a team had been watching Proxima Centauri wobble, not moving through space but wobbling in place, rocking very slightly toward us and away from us on a rhythm too regular to be noise. The wobble had a period of 11.186 days. The only clean explanation for a wobble like that is something orbiting the star and tugging on it, and when they worked out what that something had to be, the answer was a planet with a minimum mass of about 1.07 times the mass of the Earth. They called it Proxima b. It orbits at about 0.0485 astronomical units, which is roughly 7.5 million kilometers, about 1/20th of the distance from the Earth to the Sun. That sounds impossibly close, and around a star like our own it would be lethal. But Proxima is dim, around a star that faint. That tight orbit lands you inside what astronomers call the habitable zone, the band of distances where liquid water could in principle exist on a surface. Proxima b receives roughly 65% of the total energy that Earth receives from the Sun. So there it was, a rocky planet, roughly the mass of the Earth, in the habitable zone, orbiting the closest star to our own. 2 further candidates have been proposed since, a possible small world called Proxima d, announced in 2022 at about a quarter of Earth's mass, and a disputed candidate called Proxima c much further out. But it was Proxima b that changed the conversation, and it changed it almost overnight. Because a destination without a reason is a curiosity. A destination with a reason is a plan. Within months of that announcement, Breakthrough Starshot had publicly named the system as its target, a fleet of gram-scale sails, pushed by ground-based lasers to 20% of the speed of light, crossing the gap in about 20 years, and then spending another 4 years sending the pictures home. It is an extraordinary concept, and it may even work. But it is worth being precise about what it is. Starshot proposes to accelerate an object weighing less than a paperclip. It carries no fuel, no shielding, no life support, no ability to slow down, and no people. It is a camera thrown very hard across a room the size of the galaxy. The moment you decide to put a human being aboard, every number in the problem changes, and none of them change in your favour. A person requires air and water and food and warmth and shielding and space to move and something to do, and a way to dispose of everything their body produces, and all of that requires mass. Mass requires energy to accelerate. Energy requires fuel. Fuel is itself mass, which requires more energy, which requires more fuel. The rocket equation is not cruel out of spite. It is simply exponential, and exponential arithmetic does not care what you are hoping for. There is a way to feel how bad the exponential is without any mathematics. Think about the Saturn V, the largest rocket ever successfully flown. It stood 110 meters tall and weighed just under 3,000 tons on the pad. Of that 3,000 tons, the payload that actually went to the moon, the command module, the service module, the lunar module, and 3 men, was around 45 tons, roughly 1.5%. Everything else was propellant, and structure to hold propellant, and engines to burn propellant, all of it discarded on the way up. That ratio is not a design flaw. It is what the rocket equation does. To go faster you need more propellant, and propellant has mass, so you need more propellant to accelerate the propellant, and the requirement climbs exponentially rather than proportionally. The Saturn V spent 98.5% of itself to reach the moon, which is a distance light crosses in about 1.25 seconds. Proxima Centauri is 4.24 light-years away. Light takes 1.25 seconds to reach the moon, and just over 4 years to reach Proxima. That is a factor of roughly 100 million in distance, and the exponential does not care that we would prefer it did not. Which brings us to the central fact of tonight, and I want to put it on the table early because everything that follows is built on it. There is no propulsion concept that survives serious engineering scrutiny, not one, that gets a shielded, habitable, human-carrying vessel to Proxima Centauri within a single human lifetime. Every credible design lands in the same band, somewhere between 1 and 5% of the speed of light, and at those speeds, the crossing takes somewhere between roughly 100 and roughly 450 years. Sit with that for a moment, because the implication is not obvious until you say it out loud. It means that if we send a crewed ship to the nearest star, the people who leave will not be the people who arrive. Not because anything goes wrong, not because of an accident or a failure or a disaster, but because the journey is longer than a human life, and there is no version of it that isn't. The mission does not have a crew. It has a lineage. Children will be born in the corridors between the stars, and they will have children, and those children will have children, and somewhere around the 8th or the 9th or the 15th of those generations, a person who has never stood on a planet, never seen weather, never watched a horizon, will look through a window at a small red star and understand that they have arrived somewhere their ancestors chose without them. That is the concept we are going to spend tonight inside. Not the engineering, though the engineering is real and we will go through it. The people. What actually happens to a human population sealed inside a machine for 400 years, and what is waiting for them when the machine finally stops. Because the title of tonight is a promise, and I intend to keep it. There is a fate waiting for the first-generation ship to reach Proxima Centauri, and it is genuinely worse than the obvious answers. It is not that they run out of food. It is not that the ship breaks. Those are the failures we know how to imagine, and they are not the interesting ones. The interesting one is what happens when everything works. Before we go any further, I want to correct something, because there is a common assumption about generation ships that gets the history exactly backwards. The assumption is that the generation ship is a science fiction idea that engineers later took seriously. It runs the other way around. The engineers had it first. In 1928, Konstantin Tsiolkovsky, the Russian schoolteacher who worked out the fundamental mathematics of rocketry before anyone had launched anything, wrote an essay called The Future of Earth and Mankind. In it he described crude vessels travelling between the stars for thousands of years, with generations being born, living out their lives, and dying aboard. He used a phrase that has followed the idea ever since. He called it Noah's Ark. He was not writing fiction. He was extrapolating from his own equations, and his equations told him that the journey would be longer than a life. A year later, in 1929, the British scientist John Desmond Burnell published a short and remarkable book called The World, the Flesh and the Devil, in which he described a hollow spherical habitat, the structure now called a Burnell sphere in his honour, roughly 16 kilometres across, spinning to produce gravity on its inner surface, housing 20 to 30,000 people. Burnell was explicit that such a structure would not be a station. It would be a vessel, and it would travel for centuries. Then the idea went quiet for 30 years, and when it came back with weapons-grade physics behind it. Between 1958 and 1963, a team working under Ted Taylor and Freeman Dyson developed something called Project Orion. The propulsion concept was, and remains, one of the strangest ideas ever seriously funded. You drive the ship by detonating shaped nuclear charges behind a massive steel pusher plate, one after another, riding the shock waves. It sounds insane. It is also, by the numbers, one of the very few propulsion systems ever proposed that would actually work with technology that existed at the time. Dyson published a paper in 1968 called Interstellar Transport, in which he calculated that an advanced Orion vessel could reach roughly 3.3% of the speed of light. At that speed, the Alpha Centauri system is about 130 years away. 130 years. Even with nuclear bombs as an engine, even with the most aggressive propulsion concept ever put on paper by people with security clearances, the answer came back longer than a life. In 1964, Robert Duncan Enzmann proposed a design that has haunted the field ever since, mostly because of the sheer physical audacity of it. The Enzmann starship is fronted by a sphere of frozen deuterium 300 meters across and weighing 3 million tons used as fuel, pushing a habitat structure behind it carrying an initial crew of about 200, with room to grow toward 2,000. The fuel is the ship. Everything else is cargo. Then, between 1973 and 1978, came the most detailed interstellar engineering study ever completed, Project Daedalus, run by the British Interplanetary Society under Alan Bond. A team of 13 scientists and engineers spent 5 years designing a real vessel, down to component level. 54,000 tons, 2 stages, fusion propulsion burning deuterium and helium-3 ignited by electron beams at 250 detonations per second. Top speed, 12% of the speed of light. Target, Barnard's star at just under 6 light years. Transit time, about 50 years. 12% of light speed is genuinely fast. It is the fastest figure any rigorous study has ever produced. And I want you to notice what Daedalus achieved that speed by leaving out. It carries no crew, no air, no water, no food, no radiation shielding for people, because there are no people, no deceleration stage because it is a flyby. It screams past Barnard's star at 12% of light speed, takes readings for a matter of hours, and continues into the dark forever. Daedalus is fast because Daedalus is empty. In 1987, a joint NASA and United States Naval Academy study called Project Longshot took the opposite approach and designed a vessel that would actually stop, a nuclear pulse craft reaching about 4.5% of light speed, targeting Alpha Centauri b, with a transit time of roughly 100 years and a fission reactor to power instruments once it arrived. And since 2009, Project Icarus has been revisiting Daedalus with modern assumptions and modern materials. So we have a century of work. Tsiolkovsky, Bernal, Dyson, Enzmann, Bond, Longshot, Icarus. Different countries, different decades, different propulsion physics, chemical, nuclear pulse, fusion, antimatter, laser sail, wildly different political contexts and wildly different budgets, and every single one of them, without exception, when you put human beings aboard, arrives at the same answer. Somewhere between 1 and 5% of light speed. Somewhere between 1 and 4 centuries in transit. This is the part people miss. The generation ship is not a failure of imagination waiting for a clever person to come along and fix it. It is the stable conclusion that every serious designer reaches independently, from different starting points, using different physics, across 100 years. When 100 years of smart people trying to avoid an answer keep arriving at the same answer, it stops being a limitation and starts being a feature of the universe. So the question is not whether we can build a ship that crosses. The question is what happens to the people inside it while it does. And to understand that, we have to do something slightly uncomfortable. We have to stop thinking in years and start thinking in lives. Let me give you the numbers directly because they do most of the work here. Voyager One is the fastest object our species has ever placed on an escape trajectory out of the solar system. It is moving at roughly 17 kilometers per second relative to the Sun, which is about 61,000 kilometers per hour, which is fast enough that it would cross the United States in about 4 minutes. Voyager 1 left in 1977, and it has been running ever since. If you pointed Voyager 1 at Proxima Centauri and let it go, it would arrive in approximately 74,000 years. 74,000 years ago, our species had not yet reached Europe in any numbers. Neanderthals were still alive. The last supervolcanic eruption of Toba had just happened. That is how long our best real spacecraft would take, and it is not a serious proposal. It is a measurement of how far away 4.24 light-years actually is when you use the technology we actually possess. So we have to go faster, and here is what faster buys you. At 1% of the speed of light, 3,000 kilometers per second, roughly 170 times faster than Voyager 1. The crossing takes about 424 years. At 2%, about 212 years. At 3.3%, Dyson's figure for an advanced Orion vessel, about 129 years. At 4.5%, the Project Longshot figure, about 94 years. At 12%, the Daedalus figure, about 35 years. But remember, Daedalus carries nobody and does not stop. And at 20%, the breakthrough Starshot figure, about 21 years, for an object lighter than a paperclip. Now take the realistic crude band, 1 to 2% of light speed, and convert it out of years and into something a human being can actually feel. Use a conservative generation of 25 years. At 1% of light speed, the voyage spans about 17 generations. At 2%, about 8 or 9, 17 generations. Let me anchor that for you. 17 generations ago in your own family line was around the year 1600. Shakespeare was alive and writing. The telescope had not been invented yet. Galileo had not yet pointed one at Jupiter. Nobody in Europe knew that the Milky Way was made of stars. Nobody anywhere knew what a bacterium was, or what oxygen was, or that the continents moved. 17 generations is the distance between the invention of the telescope and the James Webb Space Telescope. And every single one of those generations on a ship would be born, raised, employed, partnered, aged, and buried inside the same enclosed volume, travelling toward a star their great-great-great-great-grandparents selected. And there is a detail in that comparison that I think is worth making explicit, because it cuts against the way we usually imagine progress. Somebody standing in the year 1600, looking forward 17 generations, could not possibly have predicted us. They could not have predicted electricity or antibiotics or aircraft, or the fact that we would have photographed the surface of another planet. The distance between their world and ours is not a distance of degree. It is a distance of kind, and almost none of it was foreseeable from where they stood. Now run that forward on the ship. 17 generations from departure, The society aboard will be as different from the founding crew as we are from the people who watched the first telescopes being built, except with one enormous difference. Our 17 generations of change were driven by contact. New places, new peoples, new ideas arriving constantly from outside, new materials, new problems. Theirs will be driven by nothing but themselves, inside a fixed volume, with a fixed population, using a fixed set of resources, meeting nobody. We do not have any idea what that produces because it has never happened. Every human culture that has ever changed has changed against something. Theirs will have nothing to change against except the last version of itself. There is a sentence I want to give you now, because we are going to come back to it more than once tonight, and it is the single most useful reframing of this entire problem. The ship is not a vehicle, it is a country. We use the word ship because it is the closest word we have, but it is actively misleading. A ship is something you board and then disembark from. A ship is a means. When you are aboard a ship, you're in a temporary state, a between, and you understand yourself as a person who is going somewhere. That understanding is possible because the journey is shorter than you are. Once the journey is longer than a life, once people are born aboard and die aboard without any of it being unusual, the vessel stops being transport in any meaningful sense. It becomes the place. It is where your parents are buried. It is where your children were born. It is the only geography you have ever known, the only weather, the only architecture, the only horizon. It has a population, an economy, a legal structure, a culture, a history, a set of founding myths, and a permanently fixed set of borders. That is not a vehicle. That is a country, and it happens to be moving. The people aboard it in Generation 9 are not travellers. They are citizens, and they are citizens of the only nation in human history that no one has ever emigrated from, arrived in, or visited. This distinction is not philosophical decoration. It changes every engineering answer downstream. If you are designing a vehicle, you optimize for the journey, endurance, reliability, getting there. If you're designing a country, you have to answer questions that no spacecraft engineer has ever had to answer. How many people should live here? Who decides who has children? What happens to someone who refuses to work? What do you do with a criminal when there is nowhere to send them? How do you educate a child about a planet that no living person has seen? What do you do when a generation decides they do not want to go? And underneath all of those is a colder question, the one that turns this from an engineering problem into something else entirely. The first generation chooses, they volunteer, they know exactly what they are signing up for, they have seen Earth, they have made a decision with full information and full agency, and whatever happens to them afterwards, it happens to people who chose it. The final generation arrives, whatever is waiting for them at Proxima Centauri, and we will get to exactly what is waiting, because it matters enormously. They at least receive the thing the mission was for. They see the destination. They are the point of the exercise. But between the first generation and the last, there are 15 others, and they receive nothing. They did not choose to be there, and they will not be there for the arrival. They are born into a corridor. They live an entire, complete human life inside that corridor, falling in love, raising children, arguing with their parents, doing their work, growing old, being frightened, being bored, and then they die in that corridor, having contributed their whole existence to an objective that was set before they were born and will be achieved after they are dead. Their entire lives are the transit. We do not have a good word for what that is. We are going to spend a fair amount of tonight looking for one. But before we can talk about what happens to those generations, we have to answer a much more basic question, and the answer to it is stranger and more disturbing than almost anyone expects. How many people do you actually need to start a human population that can survive for 400 years without ever adding a single new person from outside? The number is smaller than you think, and the reason it is smaller than you think is the problem. If you take a group of human beings, seal them away from all other human beings permanently, and let them reproduce only among themselves for 400 years, how many do you need at the start so that the population is still healthy at the end? This is not a new question. Conservation biologists have been asking a version of it since the 1970s, because it is exactly the question you face when a species is down to its last few hundred individuals in a fragmented habitat. In 1980, Ian Franklin and Michael Soule proposed what became known as the 5500 rule. An effective population of about 50 individuals is enough to avoid the immediate consequences of inbreeding over the short term. An effective population of about 500 is needed to retain enough genetic variation for the population to keep adapting over the long term. Later work has argued those figures are too low and should be pushed toward 101,000. When people started applying this to starships, the estimates came out wildly different, and the reason they came out wildly different turns out to be the interesting part. In 2002, John Moore at the University of Florida ran an analysis for a roughly 200-year voyage and suggested a founding crew of about 150 to 180 people. His model assumed people would delay having children until later in life, which slows the accumulation of generations and therefore slows the accumulation of genetic damage. In 2014, the anthropologist Cameron Smith at Portland State University published a paper in Acta Astronautica arguing that everyone had been thinking about this far too optimistically. His figure was on the order of 10,000 people, with 40,000 recommended as a margin, not because 10,000 is required for genetics alone, but because any real population needs redundancy against disease, accident, infertility, and the simple statistical bad luck that wipes out small groups. And then, between 2017 and 2018, the astrophysicist Frédéric Marin and the particle physicist Camille Bellouffi did something more rigorous. They built a piece of software called Heritage, a Monte Carlo simulation that models a multi-generational crew year by year, individual by individual. It tracks every person aboard. It tracks births, deaths, ages, pairings, fertility windows, and, crucially, the inbreeding coefficient of every child born. They ran it for a voyage of 6,300 years, not 400. 6,300, because they wanted to test a slow, passive vessel, the kind of ship that is actually achievable without exotic propulsion, and their headline result was this: the minimum viable crew is 98 people. 98. That is a small village. That is fewer people than work in a medium-sized office building. You could fit the entire founding population of a human civilization on a single commercial aircraft with seats left over. When that result was published, it was widely reported as good news, and I understand why. It makes the whole idea feel achievable. You do not need to lift a city into orbit. You need 98 carefully chosen people. But if you read past the number, what the paper is actually describing is not reassuring at all. Because Marin and Bellouffi's simulation only reaches 98 by imposing rules. Specific, explicit, enforced rules about human reproduction. In their model, partners are not chosen by attraction, or by love, or by preference. They are assigned to minimize kinship. The algorithm pairs people specifically to keep the inbreeding coefficient down, generation after generation. Reproduction is restricted to a defined age window. No children before a certain age, no children after a certain age. The number of children per person is capped and managed. Certain individuals are permitted to reproduce and certain individuals are not, based on where their genetics sit relative to everyone else's. The reason 98 works is not that 98 people are genetically sufficient. It is that 98 people under total reproductive management are genetically sufficient. The number is small because the freedom is small. Every degree of personal choice you add back into the system pushes the required crew size up, which is precisely why Cameron Smith, who was modelling a population living something like a normal human social life, arrived at a figure 100 times larger. I want you to sit inside that for a moment, because this is the first place tonight where the physics stops being physics. Imagine being a 19-year-old aboard this ship. You are in Generation 5. You have grown up here, everyone you know has grown up here, and you are in love with someone. And the answer to whether the two of you may have a child together is not a conversation between you. It is not even a conversation with a doctor. It is an output. It was determined by a genetic model written by people who died 300 years before you were born, running on a system that has been quietly tracking the ancestry of every human being aboard since departure day, and which knew the answer about you before your grandparents were conceived. And here is the part that makes it land properly. To that 19-year-old, this is not oppression. It is not experienced as tyranny. It is simply how the world works. It is the water they swim in. Every person they have ever known lived under exactly the same arrangement, and their parents did, and their grandparents did, going back further than any living memory. It is as unremarkable to them as gravity is to us. We do not experience gravity as a restriction on our freedom to float. We experience it as the shape of reality. The reproductive management system on a generation ship would be the shape of reality for everyone aboard, and nobody would think about it any more than you think about the fact that you cannot fly. That is what 98 means. It is not a crew size. It is a description of how much of a human life you have to remove in order to make the numbers work. And 98 is going to come back tonight, because that number does something else as well, something that does not show up until roughly generation 8, and that no amount of careful pairing can prevent. We will get there, but first the ship has to keep them alive at all, and the record on that is worse than almost anyone realizes. In September of 1991, 8 people walked into a sealed glass structure in the Arizona desert, and the door was closed behind them. The facility was called Biosphere 2, the idea being that Biosphere 1 is the Earth, and it covered 1.27 hectares under glass. Inside were 5 distinct biomes: a rainforest, an ocean with a coral reef, a mangrove wetland, a savanna grassland, a fog desert, and an agricultural zone where the crew would grow all of their own food. Around 3,800 species of plants and animals were introduced. The intention was that the 8 people inside would live for 2 years without receiving a single molecule from outside. It was the most ambitious closed ecological experiment ever attempted, and it is the closest thing we have to a real-world test of the core assumption behind every generation ship ever designed. So it is worth being precise about what happened. The oxygen started falling almost immediately. At the start, the atmosphere inside Biosphere 2 was at the normal terrestrial figure of 20.9% oxygen. Over the following 16 months, it dropped to 14.5%. To understand what that means physiologically, 14.5% oxygen is roughly the atmosphere you would experience standing at 4,000 meters of altitude. The crew were exhausted. They were suffering sleep apnea. Some of them could not complete simple tasks without stopping to rest. Eventually, oxygen had to be injected from outside, which broke closure and effectively ended the experiment as a closed system test. What makes this genuinely instructive is where the oxygen went. It was not a biological failure in the way you would expect. The designers had modelled the plants, the soil, the animals, the respiration budgets. What they had not modelled was the building. The structure contained an enormous quantity of freshly poured concrete, and curing concrete absorbs carbon dioxide. That removed carbon dioxide from the loop, which meant the plants had less to work with, which broke the balance. Simultaneously, the soil had been made extremely rich in organic matter to support agriculture, and the microorganisms in that soil consumed oxygen faster than the plant community could replace it. The oxygen did not disappear into biology. A large part of it disappeared into the walls. That is the lesson, and it is the one that transfers most directly to a starship. In a truly closed system, there is no such thing as an inert component. The structure itself is a chemical participant. Every material you build the vessel from is in the loop, exchanging with the atmosphere for as long as the loop exists. Over 400 years, materials that appear perfectly stable on any human timescale become significant reservoirs and sinks. And that was only the atmosphere. The ecology inside Biosphere 2 came apart at the same time. 19 of the 25 vertebrate species introduced went extinct within the enclosure. Every single pollinator species died, which in an agricultural system is close to catastrophic. Morning glory vines, introduced deliberately to help control carbon dioxide, escaped their role entirely and overran the food crops. Ants and cockroaches thrived beyond all expectation and became dominant. The crew lost significant body weight because the agricultural yield never met the projections, and then the human system failed too. The 8 crew members split into 2 factions that stopped speaking to each other outside of operational necessity. By the end of the 2 years, the group was functionally divided in half, with a level of hostility that participants have discussed publicly for decades since. 8 highly motivated volunteers in a facility with sunlight and a horizon and a view of a desert who knew the precise date they would be released, running for 2 years. That is the state of the art. There is one more detail about Biosphere 2 that I find harder to shake than the oxygen, and it concerns the trees. The rainforest biome inside the enclosure grew, and it grew fast, faster than the equivalent trees would have grown outside because carbon dioxide levels inside the structure were elevated, and the growing conditions were carefully controlled. From a distance it looked like a success. But the trees inside Biosphere 2 kept falling over. The reason turned out to be beautiful and slightly alarming. Trees on Earth develop a particular kind of dense, strong wood, called reaction wood or stress wood, in response to being pushed around by wind. The mechanical stress of being bent over and over throughout a tree's life is the signal that tells it to reinforce itself. There is no wind inside a sealed glass building, so the trees grew tall and fast and beautifully green, and they never received the instruction to build the internal structure that would let them hold their own weight, and eventually they simply collapsed under themselves. I mention this because it is the same principle we are going to meet again in a much more uncomfortable form, and it is worth having the picture in your head before we get there. An organism raised in an environment that removes a stress does not become a stronger version of what it would otherwise have been. It becomes a differently built thing, correctly optimized for the environment it actually experienced, and structurally unprepared for the one its ancestors came from. The trees were not sick. They were not badly grown. They were exactly right for a world without wind, and there is no such world outside the glass. There is a more disciplined data point, and it is worth giving credit where it is due. Between 1972 and 1984, Soviet researchers in Krasnoyarsk ran a facility called BIOS 3. It was tiny by comparison, 315 cubic meters, housing up to 3 crew, with the longest continuous closure being 180 days. It did not try to recreate a rainforest. It used chlorella algae cultivators for atmospheric regeneration and hydroponic wheat and vegetables for food, and it worked far better. Essentially complete closure of air and water, and roughly 85% closure of food. 85% is the best figure any human being has ever achieved in a closed ecological life support system. It is a genuinely impressive number. It is also, for our purposes tonight, catastrophically insufficient. Because a generation ship does not need 85% closure. It does not need 95%. It does not really even need 99.9%. Consider what a loss rate of 1/100th of 1% per year does across 400 years. That is a compounding 4% deficit in whatever element you are losing: carbon, nitrogen, phosphorus, water, with nowhere to get more. There is no atmosphere outside to draw from. There is no comet to mine. There is no resupply, no port, no possibility of stopping, and no possibility of turning back. Whatever leaves the loop is gone, permanently, and the loop has to keep operating for longer than the entire history of the United States 10 times over. The European Space Agency has been working on this problem since 1989 through a program called MELISSA, which breaks the loop into separate compartments, one for waste breakdown, one for photosynthesis, one for food production, so that each can be understood and controlled independently. It is careful, incremental, excellent work. It has still never demonstrated indefinite closure at crew scale, and it is not close. There is also a category of loss that nobody in the early designs modelled properly, and it is the least glamorous problem in interstellar flight. Things end up where you cannot get them back. In a closed loop, an element is only recycled if it is recoverable. Carbon locked into a structural polymer is not in the loop. Phosphorus that has precipitated out into a sludge at the bottom of a tank and hardened is not in the loop. Nitrogen that has been vented during a repair is not merely reduced, it is gone from the universe as far as the ship is concerned. Water that has permeated slowly through a seal over 80 years, one molecule at a time, at a rate no instrument aboard would ever flag, is gone. None of these are dramatic. That is exactly what makes them dangerous. A catastrophic leak triggers an alarm and gets fixed. A loss rate of a few grams a year triggers nothing, and over 400 years a few grams a year becomes kilograms, and in a system where the total inventory of some trace elements might be measured in kilograms, that is the whole supply. So the ship needs not only a functioning ecology, but a functioning inventory, a running account of every atom of every critical element and where it currently is, over 4 centuries, with 17 changes of personnel and an unbroken chain of record-keeping that cannot be allowed to have a single gap. Miss a decade and you no longer know what you have. So here is where we stand. The best sealed ecosystem our species has ever built could not keep 8 people breathing normally for 16 months. The most disciplined one could not reach full food closure in 6. And the requirement for the voyage we are describing is not merely better than those. It is effectively perfect, sustained for 4 centuries, with a population that must be fed every single day of it, inside a volume that cannot grow. There is a phrase that keeps surfacing in the literature about closed life support, and it stays with me. Everyone aboard a generation ship is swimming in a sea that they themselves are constantly making. Every breath you exhale will be breathed again by your grandchildren. Every drop of water you drink has been through the bodies of the dead. There is no elsewhere for anything to go. And the strange thing is that even if you solve all of it, even if the loop is perfect and the food never fails and the air holds for 400 years, the ship still transforms the people inside it, not through failure, through success. Because it is not just keeping them alive, it is building them. Here is a fact that should be much better known than it is. No mammal has ever completed a full reproductive cycle in space. Not one, not ever. We have flown animals. We have flown rodents on the Soviet Cosmos biosatellite program. We have flown quail eggs to the Mir station. We have run short-duration developmental experiments on the shuttle and on the International Space Station. But no mammal has ever been conceived in space, gestated in space, born in space, and raised to independent adulthood in space. It has never happened. There is no data. What little data there is not encouraging. Rodent studies flown on Cosmos produced pups with impaired writing reflexes, the automatic ability to work out which way is up and orient yourself accordingly, and vestibular abnormalities that persisted after return. Japanese quail eggs incubated aboard Mir hatched into chicks that could not orient themselves at all, tumbling and unable to feed properly. These are small samples, short durations, and simple animals, but they point in a consistent direction, and the direction is that development in altered gravity does not produce a normal animal that happens to be lighter. It produces a different animal. Now hold that against what we know about adult humans in space, which is a great deal. In microgravity, weight-bearing bone loses mineral density at roughly 1 to 1.5% per month, not per year, per month. That is a rate of loss 10 times faster than severe osteoporosis on Earth. Skeletal muscle can atrophy by as much as 20% within 5 to 11 days if no countermeasures are applied. This is why astronauts on the space station spend around 2.5 hours every single day exercising. Not for fitness, but to slow a process of decay that would otherwise leave them unable to stand on return. Then there is a condition called spaceflight-associated neuroocular syndrome, usually shortened to SANS, and it is one of the most quietly alarming findings of the space station era. In the majority of long-duration crew members, the back of the eyeball physically flattens, the optic disc swells, folds appear in the choroid layer behind the retina, vision changes, sometimes permanently. The cause appears to be the headward redistribution of fluid that happens when gravity stops pulling your blood toward your feet. Combined with altered pressure inside the skull, some crew members have not fully recovered. And then there is the NASA twin study published in the journal Science in 2019, which remains one of the most useful pieces of human spaceflight biology we have. Scott Kelly spent 340 days aboard the space station, while his identical twin brother Mark remained on the ground. 2 people with the same genome, one in orbit, one not. Among the findings, Scott's telomeres, the protective caps on the ends of chromosomes, actually lengthened during the flight and then shortened rapidly after return. More than 90% of the changes in gene expression returned to baseline within 6 months of landing, but roughly 7% did not. 7% of the changes were still there 6 months later, after less than a year in space, in a fully grown adult who had already finished developing. Now put a child in that environment, not for a year, for a life, conceived there, grown there, every stage of skeletal formation, every stage of cardiovascular development, every stage of vestibular calibration, every stage of immune training, happening in an environment no human body has ever developed in. Which brings us to the obvious objection. Surely you just spin the ship. You can, and every serious design does. Rotate the vessel, and the outward push against the hull substitutes for gravity. The problem is purely geometric, and it is unforgiving. To generate one full Earth gravity at a comfortable rotation rate of 1 revolution per minute, you need a radius of about 894 meters. That is a spinning structure nearly 2 kilometers across. If you rotate faster, you can shrink it. At 2 revolutions per minute, you need about 224 meters, and at 4 revolutions per minute, about 56 meters. But rotation is not free. Inside a rotating environment, the Coriolis effect becomes noticeable. Move in any direction other than parallel to the axis, and you are pushed sideways. Drop something, and it does not fall straight down. It curves. Turn your head while walking, and the fluid in your inner ear is thrown in a direction that does not match what your eyes are reporting. which produces exactly the sensation your body interprets as poisoning. Above roughly 2 to 3 revolutions per minute, unadapted people become severely motion sick. Ashton Graybeel's slow rotation room experiments at Pensacola in the 1960s and 70s showed that human beings can adapt to much higher rates. Subjects reach 10 revolutions per minute over a period of days. But adaptation takes time and the process is deeply unpleasant. The practical consequence, when you run the mass and structural numbers on a vessel that must also carry shielding and life support and fuel, is that a real generation ship almost certainly does not spin at 1 gravity. The designs that survive scrutiny land in partial gravity, commonly modelled somewhere between 0.3 and 0.6 of an Earth gravity. So picture a child born in the ring of that ship. She is 4 years old, she is learning to run, and to her the physics is not strange, because it is the only physics she has ever met. When she runs against the direction of the spin, she feels slightly heavier, and when she runs with it, she feels slightly lighter, and she has known this since before she could speak. She drops a cup and watches it curve gently sideways as it falls, and she catches it without thinking, because her arm learned the parabola before her brain learned language. When she turns her head sharply while walking, she feels nothing at all, because her vestibular system was calibrated in this rotating frame during the window when calibration happens, and the mismatch that would flatten an adult from Earth simply is not a mismatch for her. She is completely, effortlessly at home. Her balance is better than yours. She can jump higher than any human being in recorded history. Her body is a beautiful and perfectly functional piece of engineering, exquisitely matched to the environment that built it. And that environment is a spinning tube travelling at 2% of the speed of light through interstellar space. It is not a planet. Her skeleton has been laid down against a fraction of Earth's pull, so her bones are lighter, and her muscles are calibrated for a load that Proxima b will not respect. If you put her on the surface of the world she's being sent to, a world with roughly Earth-like gravity, she would not feel heavy. She would feel crushed. She would be trying to stand while carrying more than double her entire life's experience of her own weight. The ship is not preserving these people in transit. That is the assumption everyone makes, and it is wrong. A generation ship is not a container that holds colonists safely until they arrive. It is an environment, and environments build bodies, and this environment is building bodies for itself. Which raises a question I am going to keep circling tonight and not answer until the end. If the voyage makes them fitter for the ship, and less fit for the destination with every passing generation, what exactly is arriving? We are not ready to answer that yet, because there is something else happening to them at the same time, something invisible that never stops for 400 years. Let me step back for a moment and stack up what we have established so far, because the pieces have started to interact and it is worth seeing the shape of it before we go further. We know the distance is fixed at 4.24 light-years. We know 100 years of engineering has never found a crude design faster than a few % of light speed. We know that puts the voyage somewhere between 1 and 4 centuries, which makes it generational, which means the people who arrive are not the people who left. We know the founding population can be as small as 98, only if reproduction is centrally managed. We know the closed ecology has to be effectively perfect, and that the best one we have ever built failed in 16 months. And we know that partial gravity, applied across a whole childhood, does not preserve a human being. It redesigns one. Now add the thing that is happening constantly, everywhere aboard, from the moment of departure, that nobody can turn off. Space is not empty of energy. It is full of galactic cosmic rays, atomic nuclei that have been accelerated to relativistic speeds, mostly by supernova shock fronts, and that have been travelling through the galaxy for millions of years. About 90% of them are protons, about 9% are helium nuclei, and roughly 1% are something far worse, called HCE particles, high atomic number, high energy, which is to say the fully stripped nuclei of heavy elements like carbon, oxygen, silicon and iron, moving at a substantial fraction of light speed with all of their electrons torn away. An iron nucleus at relativistic speed is not like an X-ray. An X-ray deposits its energy diffusely. A relativistic iron nucleus punches a straight track through tissue, and along that track it destroys essentially every cell it passes through, while also knocking out a spray of secondary particles into the surrounding tissue. One particle, one continuous line of damage, potentially straight through an organ. We have measured this environment directly. The Mars Science Laboratory carried an instrument called RAD on its way to Mars, and Carrie Zeitlin and colleagues published the results in Science in 2013. Inside the spacecraft in interplanetary space, the dose rate was approximately 1.8 millisieverts per day. 1.8 millisieverts per day is about 0.66 sieverts per year. For comparison, a typical background dose on the surface of the Earth is about 2 to 3 millisieverts per year, so a person in deep space is receiving in roughly a day and a half what a person on Earth receives in a year. Over a 400-year voyage, the raw unshielded cumulative figure exceeds 260 sieverts. To put that in perspective, an acute whole-body dose of 8 sieverts delivered at once is essentially universally fatal, and it is worse than that number suggests, for a reason that is easy to miss. The RAD measurement was taken inside the heliosphere, the bubble of solar wind that surrounds our own star, during a period of relatively high solar activity, and solar activity actively suppresses galactic cosmic ray flux by pushing it out of the inner solar system. A generation ship spends approximately 0.01% of its journey inside that protection. For the other 99.99%, it is in the raw interstellar radiation field, with no star's magnetic influence shielding anything, so you shield the ship, obviously. And here is where the physics does something genuinely counterintuitive, and it is the part I find most interesting about this whole problem. Adding shielding does not smoothly reduce the dose. In a specific and dangerous middle range, adding shielding makes the radiation worse. The reason is fragmentation. When a relativistic ion nucleus strikes the nucleus of an atom in your hull, it does not simply stop. It shatters, and so does the target, and the collision produces a shower of secondary particles, lighter nuclei, protons, and critically neutrons, which spray forward into the interior. Neutrons are electrically neutral, which means they pass through most materials without interacting until they happen to hit a nucleus directly, and they are biologically very damaging. A thin or moderate shield can convert one dangerous particle into a cascade of many dangerous particles spread over a wider area. There is a valley in the middle of the shielding curve, and you must not stop in it. To get real reduction, you need mass, and specifically you need hydrogen-rich mass, because hydrogen nuclei are single protons and are much better at absorbing energy without producing heavy secondary fragments. In practice, that means water or polyethylene, and it means meters of it, and even several meters of water only reduces the galactic cosmic ray dose by roughly half. Now watch what happens to the mission when you do that. Wrapping a habitat large enough for 100 people in several meters of water is an enormous mass. Every ton of that mass has to be accelerated to cruise velocity, and, if you intend to stop, decelerated again. The rocket equation is exponential, so adding mass does not linearly reduce your achievable speed, it eats into it disproportionately. Lower speed means a longer voyage. A longer voyage means more generations aboard. More generations means a larger cumulative radiation exposure across the population, which argues for more shielding, which adds more mass, which reduces speed further, which adds more generations. That is a closed loop, and it does not have a comfortable exit. Every single hazard we have discussed tonight is solved by adding mass, and adding mass is paid for in generations. The environment is not a separate problem sitting alongside the generation problem. The environment is the reason there is a generation problem at all, and that is with the ship moving through what we cheerfully call empty space. It turns out that at these speeds, empty is not a description of the universe, it is a description of how slowly you are going. The sun is currently inside a cloud. It is not a cloud in any sense you would recognize. Astronomers call it the local interstellar cloud, and informally, with the kind of affection scientists reserve for things that are extremely diffuse, the local fluff. It is a warm, partially ionized region of interstellar gas roughly 30 light-years across, and the sun entered it somewhere between 40 and 150,000 years ago. Its density is about 0.3 atoms per cubic centimeter. Let me translate that. In the air you're breathing right now, a cubic centimeter, about the volume of a sugar cube, contains roughly 25 billion molecules. The local fluff contains, in that same volume, on average, 1/3 of one atom. It is a better vacuum than any laboratory on Earth has ever produced. And beyond the local fluff sits the local bubble, a region carved out by ancient supernovae, which is emptier still, down to something like 1,000th of an atom per cubic centimeter in places. By any reasonable standard, the road to Proxima Centauri is clear. There is nothing in the way. And now, let me tell you what happens when you drive through nothing at 2% of the speed of light. A hydrogen atom sitting motionless in interstellar space has no meaningful energy at all. But energy is relative to the frame you measure it in, and from the perspective of the ship, that atom is not sitting still. It is incoming at the ship's full velocity. At 10% of light speed, a single hydrogen nucleus arrives, with a kinetic energy of about 4.7 million electron volts in the ship's reference frame. That is a respectable energy for a nuclear physics experiment, and the ship is receiving an unbroken stream of them across its entire forward-facing surface, continuously, for centuries, with no pause and no possibility of stopping. The interstellar medium from aboard a fast ship is not a vacuum. It is a particle accelerator that someone has aimed at the bow and switched on permanently. This is a genuine and well-recognized design constraint. It contributes to the radiation load on the forward sections. It slowly erodes the surface of any leading structure through sputtering, and it means that the first several meters of the ship in the direction of travel are not habitable and never will be. The living space has to be behind something thick, and that something takes the abuse for 400 years. But hydrogen atoms are the gentle part. The real problem is dust. Interstellar dust grains are small, typically around 1/10 of a micrometer, far smaller than a bacterium, invisible in every sense that matters. They make up roughly 1% of the mass of the interstellar medium, and they are distributed sparsely enough that you could fly through the local fluff for a very long time without meeting one of any size. But the distribution has a tail, and over 400 years you sample the tail, so let us do the arithmetic on a single grain. Kinetic energy is 1/2 of the mass times the velocity squared, and it is the squared term that does all of the damage here. Take a grain weighing 1 gram, about the mass of a paperclip or a raisin. At 10% of the speed of light, that grain carries roughly 450 billion joules of kinetic energy. Converted into a unit that means something viscerally, that is equivalent to about 107 tons of TNT, 1 raisin, 100 tons of high explosive. Now scale down to something more likely. Take a speck weighing 1/10,000th of a gram, 100 micrograms, genuinely invisible, smaller than a grain of pollen, something you would not notice if it landed on your hand. At 10% of light speed it arrives carrying about 45 million joules, which is roughly 11 kilograms of TNT delivered into an area of a few square millimeters. At 2% of light speed, which is the more realistic crude cruise velocity, all of these figures drop by a factor of 25. That same 100 microgram speck now arrives with the energy of roughly 400 grams of high explosive. That is better. It is not a catastrophe. It is also still a hand grenade going off against your hull, and you will meet thousands of them. This is why every serious interstellar design includes a sacrificial forward structure. The concepts vary. Some use an ablative bow cap, a thick block of material deliberately intended to be eroded away over the voyage. Some use a Whipple shield, the same principle used on spacecraft in Earth orbit, a thin outer bumper positioned well ahead of the real hull, so that an impacting particle vaporizes into a spreading cloud of plasma that the main hull can absorb over a much larger area, rather than a single point. Breakthrough Starshot's engineering studies examined a forward-facing beryllium shield for exactly this reason, at gram scale. There have even been proposals to project a deliberate cloud of dust ahead of the vessel, to break up incoming grains before they reach anything structural. Let me put you inside one of those impacts, because the scale of it is easier to feel than to calculate. Somewhere between the stars there is a speck. It weighs 100 micrograms, and it has been drifting on the same trajectory for perhaps 400 million years, since before there were animals on land. Nothing has touched it. Nothing has come near it. It has been falling through the dark on a perfectly straight line for a length of time that is difficult to hold in the mind, and in all of that time nothing at all has happened to it. Then something approaches at 6,000 kilometers per second. The grain does not scratch the shield. It does not dent it, or embed in it, or bounce. There is no time for any of those things. The entire event is over in something on the order of a nanosecond, and mechanical processes like denting require time to propagate. Instead, the grain and an equivalent region of the shield simply cease being solid. Both are converted into plasma at temperatures of tens of thousands of degrees, a small, hot, expanding bubble of ionized matter that spreads outward across the face of the bumper, dumping its energy over a widening area until the main hull, several meters behind, receives it as a spread pressure pulse rather than a puncture. A small crater is left. It joins several thousand others, and 300 meters aft in the rotating habitat ring, a woman in Generation 6 is asleep. She feels nothing. She hears nothing. There is no shudder, no sound, no alarm, no entry in any log that a human being will ever read. The shield is millimeters thinner than it was a nanosecond ago, and there are 400 years of voyage remaining, and this will happen thousands more times, and no one aboard will ever be aware of a single one of them. This is what I find most unsettling about the physical hazards of interstellar flight. They are not dramatic. There is no moment of danger. There is only a very slow accounting running for centuries in which the ship is quietly ground down by a universe that is doing nothing to it at all. The universe is not moving. The ship is. Emptiness, it turns out, is not a property of space. It is a statement about your speed. Go slowly enough, and the void is genuinely void. Go fast enough, and the same void becomes a wall of incoming matter, and the only thing that changed is you. The ship can survive all of this. Ablative shields work, Whipple bumpers work, water shielding works. Given enough mass and enough engineering, everything we have described so far is a solved problem in principle, which is precisely why the fate we are heading toward is not any of these things. The ship arrives, the ship is fine, it is the people that the voyage does something to, and the next thing it does to them cannot be shielded against, because it is not coming from outside. It was aboard on departure day, sealed in with them, and it has been running quietly ever since. On departure day, something closes that will never open again, and almost nobody notices it happening. The hatch seals, and in that moment the genetic inheritance of every human being who will ever be born aboard that ship is fixed permanently. Whatever variation exists in those 98 people, or 500 or 10,000, is the entire genetic material available to the human line aboard the vessel from that second until arrival. Nothing new can enter, there is no outside. Every child born in the next 400 years will be assembled from a shuffling and reshuffling of exactly the same deck of cards, with no card ever added. This is called the founder effect, and it is one of the most reliably strange forces in population genetics, because it is not selection. Selection is at least comprehensible. The environment favours something, and over time you get more of it. The founder effect is not about fitness at all. It is about who happened to be on the boat. The terrestrial examples are unambiguous, and they are worth walking through because they show exactly how fast this moves. On the atoll of Pingelap in Micronesia, sometime around 1775, a typhoon killed almost the entire population. Roughly 20 people survived. One of them, believed to be the ruling chief, carried a rare recessive variant causing complete achromatopsia, total colour blindness, combined with severe light sensitivity and poor visual acuity. In the general human population, this condition affects roughly one person in 30,000. On Pingelap today, it affects something like one person in 10. The condition did not spread because it was advantageous. It spread because one man out of 20 survivors happened to carry it, and after a bottleneck that's severe, one man out of 20 is a very large fraction of the future. The Afrikaner population of South Africa descends from a relatively small group of 17th century settlers. Among their descendants, the disorder variegate porphyria occurs at dramatically elevated frequency, and it has been traced back to a specific couple who married in Cape Town in 1688. Huntington's disease similarly clusters, traceable to identifiable founding individuals. Millions of people carry a specific medical inheritance because a handful of particular people got on particular ships in a particular century. Among Old Order Amish communities in Pennsylvania, Ellis Van Creveld syndrome, a form of dwarfism accompanied by extra fingers, dental abnormalities and congenital heart defects, occurs at a rate orders of magnitude above the general population. It has been traced to a single founding couple who arrived in 1744. None of these populations were badly managed. None of them did anything wrong. They simply started small and stayed closed, and after enough generations, the accidents of who founded them became the defining characteristics of everyone. There is a detail in the Pingelap story that makes the point better than the statistics do. The condition those islanders carry does not merely remove colour. Complete achromatopsia also means the cone cells of the retina do not function, and cone cells are what handle bright light. So the people of Pingelap who carry it see best at dusk and at night, and are close to blinded by full tropical daylight. Over generations, the community adapted around that. Those affected became specialists at night fishing, working by the light of the moon on the reef, where their low-light vision was not a disability but an advantage. An entire occupational niche formed around a genetic accident that arrived on the island in one man's body during a storm in the 1770s. That is the founder effect doing its full work. It does not merely change gene frequencies. Given enough generations in a closed population, it reorganizes the society around itself. Whatever variants happen to be overrepresented become, in time, part of the culture, the professions people take, the times of day they work, the stories they tell about themselves. On a ship of 98 people sealed for 400 years, the same process runs with nothing to dilute it and nowhere for anyone to go. Now, on top of the founder effect, add genetic drift, which is the ongoing version of the same phenomenon. In any population, the frequency of gene variants changes from generation to generation partly at random, simply because not everyone has the same number of children, and which particular copies of which particular genes get passed on involves a great deal of chance. In a large population, all of that randomness averages out and frequencies stay stable. In a small population, it does not average out. It wanders, sometimes dramatically, and variants can drift all the way to fixation, becoming universal, or all the way to zero, vanishing forever, with no reference whatsoever to whether they were good or bad. Drift does not select for fitness, it selects for luck, which means that on a ship of 98 people, the human beings who step out at Proxima Centauri will be shaped, more than by anything else, by which individuals in Generation 3 happen to have surviving children. Not the best, not the strongest, not the most suited to anything, the ones whose particular reproductive lives happen to work out. 400 years of human inheritance, decided by a handful of coincidences in the first century, none of which anyone at the time would have recognized as significant. And this brings us back to that number. 98 sounded like good news when we met it. It was the reassuringly small figure that made the whole enterprise seem achievable. You do not need a city, you need a village. But 98 means something else as well, and this is the part that does not appear in the headline. 98 is not just the crew. 98 is the total genetic ancestry of an entire branch of humanity, closed permanently on departure day, from which everyone who follows must be constructed. Every human being born aboard that ship for 4 centuries has 98 ancestors, total, in every direction, forever. Now, I want to be very careful and very honest about the next part, because this is where the popular version of this idea goes badly wrong, and I would rather correct it than repeat it. You will often hear that the crew of a generation ship would evolve into a new species. That is not going to happen on a 400-year voyage. It is not close to happening. Speciation in large-bodied vertebrates typically requires hundreds of thousands to millions of years, and it requires not merely isolation but the accumulation of enough genetic incompatibility that the two populations could no longer produce fertile offspring, even if reunited. 16 generations does not do that. 16 generations is not even a rounding error on that timescale. If a ship left Earth today at 2% of light speed and arrived at Proxima Centauri with a crew of 200 people, those people could walk off the ship, meet a human from Earth, and have perfectly healthy children. They would be human in the fullest biological sense. So the dramatic version, the crew as aliens, the crew as a separate species, is fiction, and I am not going to sell it to you. But the thing that actually happens is stranger, in a quieter way, precisely because it is not fiction. It is measurable. It has terrestrial precedent. And unlike speciation, it does not need thousands of years. It needs 1 generation. Your genome is not a blueprint. This is one of the most persistently misunderstood facts in all of biology, and it matters enormously here. A blueprint specifies an outcome. If you follow it correctly, you get the building that was drawn, and if you follow it in Norway or in Nigeria, you get the same building. That is not how a genome works. A genome is closer to a set of conditional instructions, a recipe that responds to its own cooking conditions. It says things like, build bone here and keep building until the mechanical loading tells you to stop. Lay down muscle and calibrate the density to the resistance encountered. Wire the vestibular system and tune it against whatever consistent acceleration field you find. Train the immune system and set its baseline aggression against whatever microbial environment shows up in the first few years. The instructions are the same in every human. The conditions are not. and on a generation ship the conditions are unlike anything a human body has developed in for the entire 300,000-year history of our species. So let us be specific about what actually changes, because it is a longer list than most people expect. The skeleton changes first and most obviously. Bone is not inert scaffolding. It is a living tissue that is continuously deposited and dissolved in response to mechanical load. Under a fraction of Earth's gravity, the loading signal is permanently reduced, so the deposition rate is permanently reduced. An adult who moves to low gravity loses bone density from an already completed skeleton. A child who grows up in low gravity never builds that density in the first place. Their bones are not damaged. They are correctly constructed for the environment they were built in, and they are structurally inadequate for anywhere else. The cardiovascular system changes. On Earth, your heart works against a column of blood that gravity is constantly trying to pull toward your feet, and a substantial part of your circulatory architecture exists to fight that. Reduce gravity and you reduce the load. The heart of a person raised in low gravity is calibrated to a demand that Proxima b would immediately double. The vestibular system changes. The inner ear is tuned during a developmental window, and what it tunes against is the consistent acceleration field it experiences during that window. A child raised in a rotating habitat calibrates against rotation, including the Coriolis effects that would nauseate any adult from Earth. The result is not a defective sense of balance. It is a correctly functioning sense of balance for a spinning environment. The eyes change. Human vision develops against distance. The reason myopia rates are climbing sharply in urban populations on Earth appears to be substantially environmental. Children who spend their developmental years indoors, focusing on near objects under artificial light, do not develop the same visual apparatus as children who spend those years outdoors looking at horizons. A generation ship has no horizon. The longest sightline aboard might be 100 meters. Nobody aboard has ever focused their eyes on infinity, because there is no infinity aboard, and by generation 3 there may be nobody left who understands what a distant object looks like. And the immune system changes, and this may be the most consequential of all. Your immune system is not born knowing what to attack. It is trained, primarily in early childhood, by exposure to an enormously complex microbial environment. The trillions of bacteria, fungi and viruses that live in soil, in air, on other people, in food, in animals. That training is what teaches it the difference between a threat and a neighbour. We already have strong terrestrial evidence, in the form of the hygiene hypothesis and its descendants, that reducing microbial diversity in childhood produces immune systems that are miscalibrated in specific ways, more prone to allergy, to autoimmune conditions, to inappropriate inflammation. A generation ship has, by design, one of the most simplified microbial environments imaginable. It is a sealed volume with a deliberately curated ecology, no soil communities of any complexity, no wild animals, no seasonal variation, no external input of any kind. Biosphere. 2. Remember, lost 19 of 25 vertebrate species and every pollinator inside 2 years, and that was a system with an entire enclosed rainforest in it. A starship's biological community will be far smaller and will simplify further with every decade, because closed ecosystems always simplify. Species drop out. They do not come back. So by generation 5, you have a human population whose immune systems have been trained by a microbial world with perhaps 1/100th of the complexity of Earth's over 5 generations of progressive simplification. That population is not sick. Aboard the ship, in the environment they were calibrated to, they are likely healthier than we are. Fewer pathogens, no seasonal disease, no novel infections arriving from anywhere. But their immune systems have never met most of what exists on a planetary surface, and they carry no inherited familiarity with any of it. The history of human contact between isolated populations is not reassuring on this point, and I will let you draw the parallel yourself rather than dwell on it. Now, none of the changes I have just described are genetic. Every one of them is developmental, the same genome, built under different conditions, which means they appear in one generation, not 16, not 1,000. The very first child born and raised aboard is already different in all of these ways, and every subsequent generation compounds it, because each one is raised by parents who were themselves shaped this way, in a ship whose ecology has simplified a little further. There is a further layer that I want to flag clearly as speculative rather than established, because the science is genuinely unsettled. There is evidence that some environmentally induced changes in gene regulation chemical marks on DNA that alter how genes are expressed without changing the sequence itself, can be transmitted across generations in mammals. How far this extends in humans, and for how many generations, is actively debated, and I would not want to overstate it. But if it operates at all across 16 generations of a constant novel environment, it adds a heritable layer on top of the developmental one. Nobody knows. There is no data set. There has never been a multi-generational mammalian population in altered gravity, so everything past Generation 1 is extrapolation from first principles. So that is the 400-year voyage. The arrivals are unambiguously human, unambiguously the same species, and unambiguously built to a specification that no longer matches the planet they were sent to. But now let us change one number and watch what happens. Murden and Belufi did not model a 400-year voyage. They modelled 6,300 years, because that is what you get with a genuinely passive low-energy vessel, the kind that does not require breakthrough propulsion, the kind we could very nearly attempt with technology we can currently describe. 6,300 years is roughly 250 generations. 250 generations of complete reproductive isolation in a population of a few hundred under continuous novel selective pressure, with drift running unchecked the entire time. That is no longer merely developmental. That is the textbook setup for allopatric divergence, the standard mechanism by which populations separate. 6,000 years is still short for full speciation in a slow-breeding, long-lived animal, and I am not going to tell you the crew arrive as a new species even then. But 6,000 years in a population bottlenecked to a few hundred, with real selection pressure from low gravity and chronic radiation, produces divergence on a scale that has no human precedent. Human populations that have been geographically separated for tens of thousands of years show measurable genetic differentiation, and those populations numbered in the millions, with constant gene flow at the edges. Compress that into a few hundred people with zero gene flow and a novel environment, and the divergence runs orders of magnitude faster, which gives us the rule that I think is the most quietly disturbing generalization in this entire subject. The slower the ship, the more different the arrivals, and the slower ships are the realistic ones. Every step you take away from exotic propulsion and towards something we could actually build extends the voyage, and every extension deepens the transformation. The most achievable mission produces the most alien crew. The version of this we're most likely to actually attempt is the version in which the people who arrive are the least like the people who left. They will still be human, but they will be a branch of humanity that's separated from us at a specific hour on a specific day and never rejoined. That is the biological answer. It is not the whole fate, and it is not even the worst part of it, because something else has been happening aboard that ship at the same time, on the same time scale, and it is not made of genetics at all. Every human society that has ever existed has had an exit. I want to state that plainly because it sounds like an exaggeration, and it is not. Throughout the entire history of our species, in every culture, under every form of government, however brutal, there has always been a physical elsewhere. You could leave. You could walk into the next valley, cross the river, board a ship, defect, emigrate, disappear into a forest or a city or a border. It might be difficult. It might be lethal. It might mean abandoning everything you had. But the possibility existed, and its existence has shaped every political structure humans have ever built, whether or not anyone actually used it. The option to leave is the quiet foundation underneath consent. A society you could depart from and did not is a society you are, in some minimal sense, participating in. A generation ship has no exit, and I do not mean it is difficult to leave, or that leaving is heavily punished. I mean that the entire universe outside the boundary of the society is hard vacuum at 3 degrees above absolute zero, and the consequence of crossing that boundary is death within seconds. The society aboard the ship is not merely isolated. It is coextensive with survival itself. There is no elsewhere. There is no forest. There is no border to run for. And once you understand that, all of the engineering requirements we have been discussing tonight stop reading like engineering and start reading like a constitution. Reproduction must be regulated. We covered why. Unregulated population growth in a fixed volume closed ecology is lethal within a few generations. An unregulated pairing collapses the genetic model that made a small crew viable in the first place. So the ship must decide who has children, when, and with whom. That is not a policy that can be voted on and reversed, because the consequences of getting it wrong are not recoverable. Occupation cannot be fully voluntary. The ship requires a specific distribution of skills in every single generation. Engineers, physicians, agronomists, system specialists, teachers, and it cannot recruit. It cannot advertise. It cannot import a specialist. If the current generation produces nobody willing to maintain the life support systems, the ship dies and there is no correction available. So the allocation of people to functions has to be managed, which means that what a person does with their life is to some degree assigned before they are old enough to have an opinion about it. Resource allocation must be centrally controlled. There is no surplus, no external market, no possibility of production beyond what the closed system supports. Every calorie, every litre of water, every watt is accounted for. Scarcity is not a temporary condition to be solved by growth. It is permanent and structural, and descent cannot be resolved by separation. This is the one that has no workaround. On Earth, when a group within a society finds the arrangement intolerable, the ultimate release valve is division. They leave, they form something else, they go somewhere. Aboard the ship, two factions who cannot live together have no option but to continue living together, in the same corridors, sharing the same air, for the rest of their lives and their children's lives. None of this requires a villain. That is the thing I want to be clear about, because it would be much easier if there were one. Nobody in this story is a tyrant. The people who design the ship are not authoritarians. They are engineers solving a closed system problem, and every constraint they impose is a rational response to a real physical limit. The people running the ship in Generation 9 are not oppressors. They are administrators of a system they inherited, doing their best with a set of rules that predate them by centuries and that they cannot change without killing everyone. The system is not evil. It is simply, unavoidably, total. There is one further constraint that sounds minor and is not, and it concerns knowledge. A generation ship must carry in living human heads the complete practical ability to maintain every system it depends on, not the theory, the practice. And practical knowledge is not stored in libraries. It is stored in people who have done the thing, and it is transmitted by doing the thing alongside someone who already can. On Earth we lose this kind of knowledge constantly and barely notice, because there is almost always someone else who has it. We have lost the ability to build certain historical instruments, to reproduce certain alloys, to perform certain surgical techniques, simply because the last practitioners died without training replacements. It happens quietly, and it is usually recoverable, because the world is large and somebody somewhere kept the skill alive. Aboard the ship, the population of people who can do any given specialized task might be 3, or 2, or, in a bad decade, 1. If those people die before training successors, an accident, an illness, a run of bad luck in a single generation, the capability has gone permanently, and the manuals will not bring it back, because a manual has never yet taught anyone to do anything difficult with their hands. The ship does not merely have to keep people alive for 400 years. It has to keep several dozen distinct bodies of craft knowledge continuously alive in a population smaller than a village, across 17 handovers, with no possibility of recruiting from outside and no margin for a single one of them being dropped. We do have terrestrial data on how small closed communities without exit actually behave, and it is worth looking at 2 examples that sit at opposite ends of the rigor spectrum. The first is Pitcairn Island. In 1790, 9 mutineers from HMS Bounty, together with 18 Polynesians, 6 men and 12 women, most of whom had been taken aboard against their will, settled a remote and effectively unreachable island. They burned the ship. There was no departure. Within 4 years, all but one of the adult men were dead, almost entirely by violence, a sequence of killings driven by disputes over land and over the women, followed by reprisals. The community that eventually stabilized carried severe genetic and social consequences that persisted for 2 centuries, including a pattern of abuse that led to criminal trials in the early 2000s. 27 people, no exit. 4 years to near-total collapse. The second example is far more controlled and in some ways more troubling because of it. Between 2010 and 2011, 6 volunteers took part in Mars 500, an isolation study run in Moscow. 520 days sealed inside a mock spacecraft, with realistic communication delays to simulate a Mars mission. These were screened, trained, highly motivated professionals. They knew exactly what they had signed up for. They knew the precise date they would walk out. 4 of the 6 developed significant psychological or sleep disturbances over the course of the mission. One crew member's circadian rhythm drifted toward a 25-hour cycle, progressively desynchronizing him from everyone else. He was gradually living on a different day from his crewmates while sharing the same room with them. Across the crew as a whole, activity levels declined markedly as the mission went on. People moved less, did less, and withdrew, in a pattern the researchers described as behavioral hyperkinesis. 520 days, 6 volunteers, a known release date, a door that could have been opened at any moment. Now extend that to 400 years, several hundred people, no release date within living memory, and no door at all. And underneath all of it sits the thing I have been circling all night, which I now want to say without any hedging. Every human being aboard that ship after the first generation was placed there by people they never met, for a purpose they did not choose, with no possibility of withdrawal for the entire duration of their life. We have language for that situation, and the language is not colonist. It is not explorer. It is not pioneer. When a person is confined for the whole of their life in a fixed location, without ever having agreed to it, as a consequence of a decision made by somebody else, we do not usually call that a mission. I want to be careful here, because I am not trying to hand you a moral verdict. The ethics of this are genuinely argued in the literature, and reasonable people land in different places. There are serious philosophers who point out that none of us consented to be born, or to be born where we were born, or into the constraints we were born into, and that a child on a starship is in a difference of degree rather than kind from a child born into any other set of circumstances they did not choose. That argument has real force, and there is a specific place where it stops working. The rest of us are born into a world with alternatives, however difficult those alternatives are to reach. Every child born aboard that ship is born into a world where the alternative is vacuum, into a role that was structurally required before they existed, under rules that cannot be amended for a purpose that will be fulfilled long after their death. The first generation made a choice. Everyone after them inherited a sentence, and what makes it land, for me, is that they would not describe it that way. To someone in Generation 9, this is simply life. It is normal. It is the only thing that has ever been normal. They are not suffering under an obvious injustice. They are living an ordinary human existence with friends and work and love and boredom, inside a structure whose walls they cannot see because the walls are all there has ever been. The ship is not a vehicle, it is a country. And now we can finish the sentence properly. It is a country with a fixed population, an unamendable constitution, assigned occupations, regulated reproduction, permanent scarcity, no immigration, no emigration, no neighbours, no elsewhere, and no way out for anyone, ever, until an arrival that almost nobody alive will live to see. The question is what such a country does with a mission it inherited from strangers, and the answer to that is the point at which this stops being a story about physics. Language does not hold still. Read a page of English from 400 years ago and you can follow it, but you can feel it resisting you. The spelling is unstable, the grammar has joints in different places, and a significant number of words mean something they no longer mean. Go back 1,000 years to Old English, and it is not a difficult version of your language. It is a foreign one. You would need to study it the way you would study German. A 400-year voyage therefore contains roughly the linguistic distance between us and Shakespeare. That is survivable. The final generation could read the departure records with some effort, the way we read the King James Bible. A 6,000-year voyage contains more linguistic distance than exists between any two living languages on Earth, and the final generation would be able to read the founding documents only as scholars read a dead script, with commentary and reconstruction. But institutional purpose decays much faster than language does, and this is where the real damage happens. Consider what the mission actually is. From the perspective of a person in Generation 9, it is an instruction. It was issued by people who are dead, to people who never met them, concerning a destination that no living person has seen, for reasons that belong to a planet no one aboard will ever visit, and that most of them cannot really imagine. There is no external verification available for any part of it. Every single thing that anyone aboard knows about Earth, that it exists, that it is blue, that there are oceans and forests and 8 billion people, that the mission was launched from it, is a record maintained by the ship. Think about how much of your own confidence in the world rests on being able to check. You believe the ocean exists partly because you could go and look. You believe other countries exist because people arrive from them. On the ship, none of that is available. The entire history of the human species is a library, and libraries are maintained by people, and people in Generation 9 have never met anyone who had access to anything the library does not contain. The mission does not need to be actively rejected in order to fail. It only needs to become a story instead of a plan. The literature and the serious speculative treatments identify 3 broad failure modes here, and they are worth naming because they are not equally obvious. The first is that the mission becomes religion. This is the most likely one, and in some ways the most benign. The founding is remembered but ritualized. The arrival becomes prophecy rather than schedule. The systems are maintained faithfully, perhaps more faithfully than an engineering culture would maintain them, but the reasons drift from operational to doctrinal. This ship arrives on time, staffed by people who understand the maintenance procedures perfectly, and the physics not at all. The second is that the mission is forgotten. This one sounds absurd. How do you forget you are on a spaceship? But consider that after 400 years, nobody aboard has ever seen the outside. There are no windows in most designs, because windows are structural weaknesses and radiation paths. The knowledge that the enclosure is moving through space, rather than simply being the world, is transmitted purely by education. It survives only as long as the education system does, and educational systems are among the first things that erode when a society goes through a difficult century. There is a version of this ship that arrives at Proxima Centauri carrying several hundred people who do not know that arriving is a thing that can happen. The third is that the mission is repudiated. A generation looks honestly at its situation, understands exactly what was done to them, and declines. They cannot turn the ship around in any meaningful sense. The fuel is not there and the destination is closer than the origin by that point, but they can stop treating the arrival as the purpose of their existence, and they can raise their children not to. All 3 end in the same place. The vessel arrives. The mission does not. And now I want to introduce the last piece, because it is the one that reframes everything else, and it is the piece almost nobody sees coming. In 2006, a researcher named Andrew Kennedy published a paper in the Journal of the British Interplanetary Society with a title that sounds dry and is not: Interstellar Travel, the Weight Calculation and the Incentive Trap of Progress and Revolutions. Kennedy's observation is this: the maximum speed our species can achieve has not been constant. It has grown, and it has grown roughly exponentially as new propulsion technologies have arrived. If you fit a curve to the history of maximum achieved spacecraft velocity, you get a growth rate on the order of 1.4% per year. Now apply that to an interstellar voyage. Suppose you launch today at 2% of the speed of light on a 400-year crossing to Proxima Centauri. Meanwhile, back on Earth, technology continues to improve at that same 1.4% per year. In 100 years, the achievable velocity has roughly quadrupled. A ship launched a century after yours, travelling at 8% of light speed, takes about 106 years to make the crossing. It departs 100 years behind you and arrives roughly 200 years ahead of you, and a ship launched 200 years after yours arrives earlier still. Kennedy worked the mathematics through properly and found that for many destinations there is an optimal departure time, and it is usually not now. For Barnard's star, using his assumptions, the optimal wait before launching was on the order of 700 years. Leave before that and you are not being bold, you are being overtaken. He called it the incentive trap, and the trap has teeth in both directions. If you always wait for better technology, you never leave at all, because there is always something better coming. But if you leave too early, you condemn 17 generations of human beings to a voyage that a later, faster ship will render pointless while they are still in the middle of it. So let me put you inside that. The ship is 220 years out. It is Generation 9. The ship is functioning well. The loop is holding. The shielding is intact. The population is stable. The society is doing whatever it has become. And a signal arrives. It has been sent from Earth, and it is old, but it is not that old, because light crosses in 4 years and change while the ship has spent 2 centuries covering the same ground. And the signal contains, among the routine archive updates, the news that a vessel departed the solar system 80 years ago at 11% of light speed, and that it made planetfall at Proxima Centauri 31 years back, and that there is a functioning settlement there now with a population in the thousands, and that they are very much looking forward to receiving the generation ship when it arrives in 180 years. Nobody has done anything wrong. Nobody has failed. The ship is not damaged. Every single system has worked exactly as designed. The crew have upheld the mission perfectly for 9 generations, and the mission is over. It ended while they were asleep, and nobody aboard was even present for it. What do you tell Generation 10? What is the purpose of the reproductive management protocol now? What is the point of the training programs, the maintenance rotations, the entire architecture of meaning that a whole civilization has been built around? You're no longer a colony ship. You're a very slow vehicle carrying several hundred people toward a place that does not need them, populated by their own distant cousins who will regard them as a historical curiosity. People from the past, arriving late, physically unable to walk on the world their descendants' cousins have already been living on for 2 centuries. Let me give you the moment I cannot stop thinking about. There is a navigator in the 9th generation, and part of his routine is a positional check using the aft star field. He locates Saul, confirms the angle, logs it. It takes him under a minute. It is the most boring task in his week. His grandmother had the same job, and when she did it, Saul was the brightest thing in the aft field by a wide margin, unmissable, the first thing your eye found. A beacon you could not look away from, and everyone aboard knew what it was. For him it is not easy to find. He needs the instrument overlay. The ship is now well over 2 light-years out, and from here the sun has faded to something like an ordinary star, and the aft field is crowded, and it takes him about 30 seconds of searching to be sure he has the right one. When the overlay confirms it, he looks at a modest yellow point of no particular distinction, sitting in a crowd of similar points, none of which are remarkable in any way. He holds it for a few seconds longer than the procedure requires. He is not sad. He has no attachment to it. He has never seen it as anything other than a reference marker, and he has certainly never seen it as a sun. He is simply noticing something. His grandmother told him it used to be obvious, and that is the moment when 4.24 light-years stops being a distance, because we have been treating that number as a measurement all night, and it is time to stop. 4.24 light-years is not a length. It is 17 complete human lives laid end to end, each one whole, each one containing everything a human life contains. First words and last words, love and grief and boredom and ordinary Tuesday afternoons, and every one of them spent entirely inside the same structure, in service of a destination that none of them will see. That is what the distance actually costs, not fuel, not shielding, not engineering. Lives, in their entirety, spent as fuel, and they are spending them to reach a place that we should now, finally look at honestly. Because everything we have said so far has assumed the destination is worth arriving at. It is time to find out whether it is. Proxima Centauri is a small star, and small stars are violent in a way that our own sun has taught us not to expect. This is genuinely counterintuitive, so it is worth explaining why it happens. Red dwarfs are fully convective. They do not have the layered structure our sun does, with a radiative zone separating the core from the convective envelope. The entire star churns, from centre to surface, like a pot at a rolling boil. That churning drags magnetic field lines through the star and tangles them relentlessly, and when tangled magnetic field lines snap and reconnect, they release energy. On a star with 12% of the sun's mass, the energy released is enormous relative to the star's ordinary output, because the ordinary output is so low. The result is that Proxima Centauri, a star you cannot see with your eyes, throws flares that would be difficult to survive anywhere nearby. In May of 2019, a coordinated observing campaign involving 9 instruments, including ALMA in Chile, the Hubble Space Telescope, and TESS, happened to be watching Proxima Centauri when it produced something extraordinary. Meredith McGregor and colleagues published the analysis in Nature Astronomy in 2021. Over the course of approximately 7 seconds, the star brightened by a factor of roughly 14,000 in the ultraviolet, 14,000 times brighter, in 7 seconds, from a star with 1/8 of the sun's mass. The sun produces flares too, and large ones are serious business. The Carrington event of 1859 remains the reference case, and a repeat today would do significant damage to electrical infrastructure. But nothing our sun has ever been observed to do is within orders of magnitude of what Proxima did in 7 seconds in 2019. And this was not a once-in-an-age event caught by luck. Proxima flares constantly. Smaller flares occur on timescales of hours. The star is one of the most active flare stars in the solar neighbourhood, and it has been doing this for the entire 4.5 billion years it has existed, and it will keep doing it for the next 4 trillion. Now remember where Proxima b sits, 0.0485 astronomical units, 7.5 million kilometers, 1/20th of the distance from Earth to the Sun. Mercury, our closest planet, orbits at about 0.39 astronomical units. Proxima b is 8 times closer to its star than Mercury is to ours. Modelling work following the 2016 discovery, including studies by Ignacio Ribas and colleagues, and by Cecilia Garafo and colleagues, estimated that Proxima b receives on the order of 400 times the X-ray flux that Earth receives from the Sun. The stellar wind pressure at its orbit may be thousands of times what Earth experiences, and this has been going on not for a few million years, but for billions. An atmosphere is not a permanent feature of a planet. It is a balance between what a planet's gravity can hold and what its star is stripping away. High-energy radiation heats the upper atmosphere until the fastest molecules exceed escape velocity, and the stellar wind physically scours the top layers away. This is not speculative. It is exactly what happened to Mars, which lost most of its atmosphere to solar wind stripping over billions of years once its magnetic field shut down, a process that the Marvin mission has measured directly in progress. Now do that to a planet 8 times closer to its star than Mercury, under 400 times the X-ray flux, for 4.5 billion years. The honest scientific position is that we do not know what state Proxima b's atmosphere is in, because we have never directly observed it. The planet was detected by the wobble it induces in its star, not by transiting across its face, so we have no transmission spectrum and no direct compositional data at all. It is possible the planet retained a thick atmosphere. It is possible it was resupplied by volcanism. It is possible a strong magnetic field protected it. But the models, run repeatedly by different groups with different assumptions, keep arriving at the same uncomfortable answer. The most probable state of Proxima b, after billions of years at that distance from that star, is airless, or very nearly so, a stripped rock. It is worth pausing on how little we actually know about this planet, because the gap between public perception and the observational record is wide. Proxima b was found by the radial velocity method. That means we never saw it. What we measured was Proxima Centauri moving toward and away from us by a few meters per second, walking pace, on an 11.186-day rhythm, detected as a tiny periodic shift in the wavelengths of the star's light. From that shift you can derive an orbital period and a minimum mass, and that is very nearly the entire list of things you can derive. We do not know the planet's radius, because it does not transit. From our angle it never passes in front of its star, so it never blocks any light, so there is no shadow to measure. Without a radius we do not know its density, and without density we do not know whether it is rocky at all rather than a small gas-rich world. We do not have a transmission spectrum, which is the technique that reveals atmospheric composition by watching starlight filter through a planet's air during a transit, because again, there is no transit. And the mass figure is a minimum, not a measurement. Radial velocity only detects motion along our line of sight, so if the orbit is tilted relative to us, the true mass is higher, potentially much higher. What we have in total is a period, a distance, and a lower bound on mass. Everything else, the rocky surface, the possibility of water, the Earth-like character that made the 2016 announcement land the way it did, is inference from models, and the models are good, but they are models. And there is a second feature, which is close to certain rather than merely probable. At that orbital distance, tidal forces are overwhelming. Over astronomical timescales, they slow a planet's rotation until it matches its orbital period, which is what happened to our own moon, and it is why you have never seen the far side of it without a spacecraft. Proxima b is almost certainly tidally locked, or possibly caught in a resonance where it rotates a small whole number of times per orbit. A tidally locked world is a genuinely strange place, and it is worth taking a moment inside it. One hemisphere faces the star permanently. There is no sunrise there, no sunset, no night, no day, no seasons, and no passage of time visible in the sky at all. The star hangs at a fixed point above you and does not move, ever, for the entire history of the planet. If you stand in one spot, the shadow you cast will be the same shadow, in the same direction, at the same length, forever. The other hemisphere faces away permanently. It has never seen the star. Unless the atmosphere is thick enough to circulate heat around the planet, the night side is cold enough that atmospheric gases freeze out of the air and fall as snow, which then never sublimates, which removes them from circulation permanently. A runaway process that can strip an atmosphere from the inside even if the star does not strip it from the outside. And between the two hemispheres runs a ring. The terminator, a permanent band of twilight encircling the entire world where the star sits forever on the horizon and never rises or sets. If Proxima b is habitable anywhere, most models suggest it is habitable in that ring, in a narrow zone of perpetual dusk between a hemisphere of unmoving glare and a hemisphere of unbroken frozen dark. That is the destination. Not the world in the announcement graphics from 2016, which showed a blue-grey sphere with a hint of ocean and a horizon and a small red sun rising over it. Those images were artists' impressions, always clearly labelled as such, and they were not dishonest. But they were painted before we knew about the flare of 2019, and before the atmospheric modelling had matured, and they are what the crew grew up looking at. There is something particularly cruel in the arithmetic here, and I want to make sure it lands. Our knowledge of Proxima b will improve enormously over the coming decades. Ground-based, extremely large telescopes and next-generation space observatories may be able to characterise it directly. We might know within 30 years whether it has an atmosphere at all. But a generation ship launched today does not benefit from that. It launched with the 2016 picture, and the information will keep arriving during the voyage. That is the thing. The ship remains in contact, radio still crosses in 4 years and change, and every decade of the voyage brings better data about the destination. Which means there is a version of this story in which, somewhere around Generation 4, a routine science update arrives from Earth, confirming that Proxima b has no atmosphere, no ocean, no possibility of a surface settlement of any kind, that the world the ship was launched toward and around which an entire civilization of several hundred people has organized every aspect of its existence, is a bare irradiated rock with a permanent day side, a permanent frozen night side, and a ring of twilight in between. And the ship keeps going. Because it has to. Because there is nowhere else to go, and not enough fuel to change destination meaningfully, and turning around would take just as long as continuing. 12 more generations, travelling toward a place that everyone aboard now knows is not what they were told it was. So we have arrived at the question the title asked, and I have withheld the answer for the whole of tonight, and it is time to give it to you properly. What is the terrifying fate of the first-generation ship to reach Proxima Centauri? The answer is not one thing. It is 5, and they arrive together, and the reason it is terrifying is that not a single one of them is a failure. Here is the first, and it is the simplest, and it is the one the whole voyage is built on. Nobody who leaves survives to arrive. That is not a risk. It is not a possibility. It is the operating specification. The mission is designed, from the first line of the first document, around the certainty that every person who volunteers for it will die in transit, along with their children and their children's children, and roughly 14 further generations after that. There is no version of this that goes well enough to avoid it. The best possible outcome, perfect systems, perfect health, perfect society, flawless navigation, arrival exactly on schedule, still consists of 17 consecutive generations of human beings being born, living and dying inside a machine. Success looks exactly like that. There is no other shape available. Here is the second. The people who do arrive cannot use what they find. We walk through this, but let me put the pieces together in one place. Their skeletons were built against a fraction of Earth's gravity and have never been loaded properly. Their cardiovascular systems are calibrated for a demand the destination will immediately more than double. Their vestibular systems were tuned in a rotating frame, and a planet does not rotate the way a habitat ring does. The Coriolis environment they were built for simply does not exist on a planetary surface, and its absence would be as disorienting to them as its presence would be to you. Their eyes have never focused on anything further away than the length of a corridor. Their immune systems were trained by a microbial community that has been simplifying for 4 centuries inside a sealed box, and they have no inherited familiarity with a planetary biosphere of any kind, hostile or otherwise. Put a person from Generation 17 on a world with roughly Earth-like gravity, and they do not feel heavy. They cannot stand. They are attempting to support more than twice the weight their body has spent its entire developmental history learning to support, with a skeleton that was never given the mechanical signal to build for it. Assisted, braced, medicated, they might manage. Their children, if born on the surface, would be fine. That is the thing, the plasticity runs both ways. But the generation that arrives, the generation that the entire 400-year enterprise was for, arrives physically unable to inhabit the thing it was sent to inhabit. Here is the third. The destination is probably not there, not gone, not destroyed, simply not what the departure documents described. Most likely a tidally locked airless or near-airless rock with one hemisphere in permanent glare, one in permanent frozen dark, a ring of twilight between them, sitting 8 times closer to its star than Mercury is to ours, under 400 times the X-ray flux Earth receives, orbiting a star that can brighten 14,000-fold in 7 seconds, and does something like it regularly. A settlement there is not a matter of stepping out onto a new world. It is a matter of building, from scratch, on a hostile surface, a sealed enclosed habitat with a closed ecology. Which is to say, after 400 years of travel, the best available outcome at the destination is to construct, at enormous cost and risk, a slightly worse version of the ship they are already living in. Here is the fourth. They may have been overtaken. This is Kennedy's incentive trap, and of all the fates it is the one with the strangest emotional flavour, because there is no danger in it at all. Nothing threatens them. They simply become obsolete while in motion. A vessel that did not exist when they departed passes them somewhere in the dark without either ship ever knowing, and reaches the destination generations ahead of them. The mission is completed by someone else while its own crew are still 9 generations from arrival. Everything continues to function perfectly. The purpose is simply removed from underneath a functioning civilization, and there is nothing anyone aboard can do about it, and nothing anyone did wrong. And here is the fifth. This is the one I think is genuinely the fate, and it is the one that almost never gets discussed. They may not want to land, not out of fear, not out of cowardice or exhaustion, or a failure of nerve, out of an entirely clear-eyed assessment of their own situation, arrived at by people who are not confused about anything. Because consider what 4 centuries have actually produced. It has produced a population whose bodies were built by the ship and are optimized for it. It has produced a culture that is 400 years old and entirely self-generated, with its own history, its own founding stories, its own art, its own dead, its own meaning. It has produced people for whom the corridors are not confinement but home, in the full and unironic sense. The place their parents are buried, the place their children were born, the only geography, the only architecture, the only weather they have ever known or wanted. And there is something else it has produced which is easy to overlook because it does not sound like a hazard. It has produced competence. By generation 17, this population is extraordinarily good at the one thing they have ever done. 4 centuries of continuous operation have refined every procedure, every handover, every maintenance cycle, every crop rotation, every medical protocol. They have solved problems the founders never anticipated, and they solved them without help. They know their world in a way no human population has ever known a world, completely, down to the last valve, because it is finite, and they have had 400 years to learn all of it. A people that competent, in a system that functions that well, does not experience arrival as rescue. That is the assumption baked into every departure-era document, that the crew will be waiting, straining toward the destination, desperate for it. But the founders were imagining the feelings of people who had left Earth. The people at the far end never left anything. There is nothing in their experience that corresponds to homesickness, and nothing that corresponds to relief, and it has produced a mission that belongs to strangers. The people who chose this have been dead for 350 years. Nobody aboard has met them. Nobody aboard voted for it. The reasoning that produced the mission was reasoning about a planet none of them have seen, conducted in a language that has drifted, in a context that no longer exists. So the ship arrives, and the crew go to the observation surface, and for the first time in 400 years human beings look directly at the thing they were sent to. Here is what they see. A small star, dim and orange-red, throwing hard light without warmth. It does not look like the sun in the archives, it looks like a coal, and near it, a world. Not blue, not white, not the sphere from the departure-era images that every child aboard grew up looking at. A dull red-brown disk, half of it burning under a star that never moves, half of it black and frozen, and around the edge between them a thin bright ring of permanent dusk where the star sits on the horizon, and has sat on that horizon for 4.5 billion years. Nobody says anything for a while. There is no cheering. Whatever they were carrying about this moment, inherited across 17 generations, does not survive contact with the object itself. And then somebody says the thing that everyone has been not saying for about 2 generations now. Why would we go down there? It is not a rhetorical question, and it is not defeatism. It is a serious operational assessment, and every part of the answer supports it. The surface would kill them. Their bodies cannot function in that gravity. There is no atmosphere to breathe and probably never was. Building a habitat down there means constructing, under flare bombardment, on a hostile surface, with limited resources and no margin for error, a closed ecology that is objectively inferior to the one they are currently sitting inside, the one that has been running successfully for 400 years and that they understand completely. The ship works. The ship has always worked. Everything they need is here. Everything they are is here. And that is the fate. That is the answer the title promised, and I want to state it plainly. The terrifying fate of the first-generation ship to reach Proxima Centauri is that the voyage succeeds completely, and in succeeding quietly destroys the reason for itself. It does not fail. It does not break apart or run out of air or fall into the star or dissolve into violence. It works. It works so well for so long that it stops being a journey and becomes a home, and it builds a people so perfectly adapted to itself that those people rationally decline the only thing it was built to give them. Every generation ship is a machine for converting colonists into a crew that does not want to be colonists. And it does that not as a malfunction, but as its central and unavoidable function. The better it works, the more completely it does it. So the decision gets made, and it is not dramatic. There is no vote in the sense we would recognize, no crisis, no mutiny. There is a long conversation lasting some years, a scientific program established in orbit, some instruments deployed, some records transmitted back toward a sun that is now a fairly ordinary star in the aft field, and then a course adjustment, and the ship continues, and they were right. That is the part I cannot get past. Given everything that is true of their situation, they made the correct decision. It is the only reasonable call available, and it means that 400 years and roughly 17 generations and every single human life spent entirely inside that structure produced a flyby. 4.24 light years. We began with that number as a measurement. Then it became a duration, and then a cost, and now let me give it to you one last time as what it actually is. 4.24 light years is the exact distance at which a human civilization stops being able to send itself anywhere. It is not far enough to be impossible. It is not close enough to be survivable in a life. It sits precisely in the gap where the journey is achievable and the journey's purpose is not, and it is the nearest star. Everything else is further. And 98. We met that number as good news, the reassuringly small crew that made the whole idea feel within reach. Then it became the closed genetic inheritance of everyone who would ever be born aboard. And now, finally, it is this. 98 people, most of whom will not be remembered by name in the ship's own records, whose choices on a single day determined the entire content of 17 generations of human lives. 98 people decided everything about several thousand other people who did not exist yet and would never be asked. The ship is not a vehicle, it is a country. And this is where that sentence finishes, because you do not abandon your country because you have arrived somewhere. That was never a thing anyone was going to do. Everyone who designed the mission thought they were building transport. They were building a homeland, and a homeland does not dissolve itself on schedule because a document from 4 centuries ago says the journey is over. Now, I want to end honestly, because it would be easy to leave this as despair, and I do not think despair is the right reading. None of this makes interstellar travel impossible. It makes one particular approach to it, the crude multi-generational vessel, much stranger and much more morally complicated than the version we usually tell ourselves. There may be other routes. Uncrewed probes cross beautifully and cheaply, and Starshot might genuinely fly this century. Automated systems could build infrastructure ahead of any crew. If something like extended hibernation ever works, the generations problem changes shape entirely. And if propulsion ever reaches a genuinely relativistic regime, time dilation stops being a rounding error and starts being an ally. But there is a possibility underneath all of this that is worth sitting with, and it may be the largest idea in tonight's story. We have spent decades listening for other civilizations and hearing nothing. And one candidate explanation, speculative, unproven, but taken seriously, is not that intelligence is rare, or that civilizations destroy themselves, but simply this, that the gap between stars is exactly wide enough that crossing it requires spending generations, and generations cannot be spent without producing a population that no longer wants what it was sent for. Not a wall, not a barrier, just a distance calibrated so precisely that every civilization that tries it succeeds at the voyage and fails at the purpose, arrives intact and unrecognizable, and quietly decides to keep flying. If that is true, then the silence is not empty. It is full of ships, all of them working perfectly, none of them stopping. There is a last thing, and then I will leave you. If we ever do this, and I suspect that eventually in some form we will, then somewhere out there, at some point in the future, there will be a person in the 9th generation performing a routine positional check, and they will find, in a crowded field of unremarkable stars, one modest yellow point of no particular distinction. They will confirm the angle, they will log it, and they will hold it for a second or two longer than the procedure requires, because their grandmother told them it used to be obvious. Sleep well.